Hey everyone, Mr. Newman here, and today we're going to do the fundamental theorem of calculus. This is actually one of the most important theorems in calculus, and it really connects the derivative of what we've been doing to the antiderivatives or to the integral that we've been working on, right? So just as a reminder, recap, remember that indefinite integrals, we've worked with these already, they actually just find a formula, right? I'm going to type here because it's a little faster, formula, which is the antiderivative, right? And oftentimes we use capital F to represent this, right? F of x, okay? So that's what the indefinite integral finds. Here, we're going to use a definite integral. And just by way of reminder, so that's another thing. So indefinite integral looks like this, f of x dx. But the definite integral, okay, the definite integral looks like this, where you have a to b. And we've been writing this notation to talk about Riemann sums, but we haven't actually evaluated these exactly yet. And so, well, yeah, let me say a few more things about this before we get into that. So definite integrals, they can represent one of two things, okay? Before now, we've been working mostly with area under the curve. Okay, so that's one way to think of this. You have a function, and the area under that function, between that function and the x-axis, is the integral, is the definite integral, right? Another way to think of this is the accumulation of change, okay? So if you have a rate, such as velocity, then the integral would be the change in position, right? Or if you have a rate of, say, something being produced, then the integral is the amount produced over a certain amount of time, okay? So you can evaluate a definite integral by one of the following ways, and this comes back to what we've been talking about, the link sheets, okay? So first of all, you can evaluate it graphically, meaning you can look at the graph, and with geometry of the area under the curve, okay, you can actually calculate it either exactly or approximate it pretty well. You can also calculate it tabularly, okay, that means with a table, right? Using a table. And that would be using a Riemann sum or trapezoidal sum, right? You can calculate it that way. And of course, that's very interconnected. We start off graphically to show you how the Riemann or trapezoidal sum works and what that looks like, right? And the last way is analytically, and that's algebraically with antiderivatives, right? So just as a way of pointing out, remember these are like three of the main components of the link sheet, right? Graphs, tables, and the equations. And so just as a reminder of the different ways you can evaluate them, right now what we're going to work with, the fundamental theorem particularly talks about, it's an analytical way to evaluate definite integrals. So let's get this in here. This is one of the things you want to memorize, and I want to include one other thing here. So first of all, when you're given a definite integral here, like we wrote right above, evaluated on from a to b, okay, that's the same as capital F of b minus capital F of a. Now what is capital F? That is the antiderivative, right? So just a reminder, capital F is the antiderivative of lowercase f, right? That's what this means right here, where f, capital F prime is equal to lowercase f, okay? I also want to include one other step here that I'm going to be using and showing you guys, and this is just a bit of notation that's often used, okay? This is the same thing as capital F, and if you draw a vertical line here with b on the top and a on the bottom, it just means capital F, antiderivative, evaluated at b, and then subtract evaluating at a. What does that mean? That means just plug in b and then subtract plugging in a. That's exactly what this means right here, okay? So this is just notation to get your ducks kind of in a row before you actually go and plug all of it in, okay? So I will be using that here. Another way of writing this, of course, if we take this instead and talk about the derivative, or sorry, the integral of something that is a derivative, then you can write it like that, and then you're just talking about the original function, subtracting, evaluating it at b, subtracting, evaluating at a. And then if you rearrange that, you can also rewrite it like this, which is what we'll use later when we use the real world applications. Okay, it's a little more helpful to have that form in there. But one of the things you need to notice is you always plug in the top one first and then subtract the lower one. That's going to come in. We're looking at a few examples where we switch that around and look what happens there. Okay, so let's start with some of these practice problems, and you'll see this is very similar to what you've already been doing. We're just plugging in some numbers at the end of it. Okay, so here we have the antiderivative of x. I'm going to use the power rule. So we add 1 to the numerator, and we divide by that number. Okay, now I draw a vertical line to say, hey, we need to evaluate this from 1 to 2. So in other words, this is a way of saying, take 2, plug in 2, subtract, plugging in 1, right? So let's actually do that. So we plug in 2, and then we're going to subtract, plugging in 1. Let's see, 2, that's 4, 2 squared is 4, over 2 is 2, so we get 2 minus half, which is 3 halves. Okay, and that's one of the things before, when you did an indefinite integral, you always got a formula. Now that you're doing definite integrals, you will typically get a value or a number out of it. Okay, so here we go. Let's go on to the next one. We have integrating from 0 to 3 of 9 minus x squared. Here the 9 minus x squared is the integrand, so let's take the integral of that. So the integral of a constant is 9x. And then we're going to use the power rule here, add 1 to the power and divide by that number. Now we're going to evaluate that from 0 to 9. You'll see oftentimes it's very nice evaluating starting at 0, because as you can see, oops, I said 9, I meant 3, I'm sorry. As you can see, when you plug in 0 here, it's going to be 0. I'm going to write that down for our notes. But when you're doing problems, you do not need to write that step down. So let's first plug in 3 everywhere. Put all that in big parentheses or brackets if you like that kind of notation. Oh, and here we go. 9 times 0 minus 0 cubed, all in parentheses. Of course, all of this is just 0. So we really get 9 times 3, which is 27. Minus 3 cubed is going to be 27, but divided by 3 is 9. And then we subtract those and we get 18. Of course, here I just subtracted 0 as a way of reminder. Oops. There we go. And we get 18. All right. Moving on, you'll often see trig in here. So the antiderivative of cosine is sine. So we're really going to take sine and evaluate it from 0 to pi over 2. So what does that mean? That means sine of pi over 2 minus sine of 0. Sine of 0 is 0 because that's where the sine function starts. Sine of pi over 2 is going to be 1. And we get 1 minus 0, or just 1. There we are. Okay. Moving along, I'll let you guys try this one. Be careful, remember 1 over x is one of those special ones. Alright, hopefully you remember that that antiderivative of 1 over x is the natural log of x. Put that in absolute value bars, so here it does not matter. And we evaluate that from 1 to 2. One comment as we're doing this, I hope you all noticed, we actually don't have to write plus c, add our constant. And the reason for that is because, well, a few reasons. One way you can think of it is when you're subtracting these, the constant actually subtracts out because you're evaluating at 2 different places, okay? The other thing is you just have to know for indefinite integrals, you always must add that constant, but for definite integrals, it actually never shows up in your final answer here. So, so let's plug in 2 first, natural log of the absolute value bar of 2, minus natural log of, of 1. Now one thing, what is the natural log of 1? Well, the natural log of 1 is 0, so this is just going to be the natural log of 2. And I don't even need the absolute value bars because 2 is a positive number already. Alright, here, this should look vaguely familiar. Of course, we did this up here, just the upper bound and lower bounds are switched here. So let's evaluate this, and I'll show you guys a fast way to do this if you've calculated this before. So add 1 to the numerator, divide by 2, we already did that. We're evaluating from 2 to 1 this time, going the opposite direction. And if we plug in 1 first, it's very important to recognize you're not just plugging in the bigger number first, you're plugging in the top number first, right? Minus, plug in the lower bound. And what do we get? We get 1/2 minus 2, which is -3/2. Okay, and that's of course the opposite of positive 3/2. We could have known that because we know that when you switch the lower bound and upper bound, you actually end up with just the opposite function, right? So this is the same as the opposite of the integral from 1 to 2, which of course would then be the opposite of what we got before. So we knew that was going to happen. We could have guessed from our antiderivative rules, but it's good to evaluate that and point out it's very important, beware of plugging these in the correct order. Make sure you do the upper bound first and the lower bound second, not just the biggest number first, right? Of course, you can always switch them and then have the bigger number first. Just make sure you put that negative out in front. Moving on, here we go. So I'm first going to rewrite this. This is going to be helpful to rewrite it as 6 times x to the -2 minus 1 dx. And now I can evaluate it. So it'll get a little messy. Let's see here. We have 6. Let's add 1. Go to the plus -1. All divided by -1. Minus 1x, or just minus x. So we're evaluating this from 2 to 5. So we're going to plug in 5 first, right? So -6. I'm just going to bring this negative out in front. I mean, it's divided by -1 is the same as multiplying by -1, right? So we have 5 to the negative first, minus 1 times 5. All of that minus, plug in 2 here, we have -6. 2 to the negative first, minus 2. Now be careful you put all of that in parentheses right there and there, because that subtraction needs to get distributed, right? If you don't distribute that correctly, you'll end up with the opposite somewhere that you did not mean to. So 5 to the negative first is 1/5, so we get -6/5 minus 5. Let's see, negative is going to be plus. 6 divided by 2 is 3, and we get a plus 2 there at the end. 3 plus 2 is 5, -5 plus 5 is 0, so our answer is -6/5. There we go. All right, 2 more to do here. This one, I know it's a little messy. My mind started going to U substitution, but I thought, no, let's just simplify this integral first, okay? So I'm going to take this, think of that as x to the 1/2. And when you divide, remember you are subtracting the exponents. So it's really going to be, we still want to evaluate it from 16 to 25, right? Excuse me. But it's going to be 3x to the 1/2, because to the 1 power minus 1/2 is 1/2, minus 2x to the -1/2, because x to the 0 minus 1/2 is -1/2, dx. So we're going to integrate it, and when we integrate it, we get 3x, let's see here, add 1 up there, x to the 3/2 divided by that same number, minus 2, add 1 to the power, and divide by that same number. All of that is going to be evaluated from 16 up to 25. Whew. All right, let's plug all this in. Oh, I think we got some room here. Yeah, so we have 3. Let's see, I'm going to flip this, so it's, instead of 3/2, it's times 2/3, right? Which 3 is going to divide out. So we really get 2. 25 to the 3/2, that's going to be nice because I can do the square root first. Square root of 25 is 5. 5 cubed will be 125. I get ahead of myself though, we should stop that. Okay, minus, dividing by half the same as multiplying by 2, so that's really going to be a 4. 5 to the 1/2 power. All of that minus all the same stuff, but this time we're doing 16 instead of 25. I said that. I was saying 25 to 1/2 is 5. I need to write the 25 down first, though. Okay, does this look good? That looks about right. Okay, so then we have 4 times 125 minus 4 times 5 minus 2 times... okay, so again, I can do the 1/2 power first. So 16 the square root of 16 is 4. And then cube it. 4 cubed is 64. Also known as 16 times 4, right? Then plus 4 times 4, 16 there. So we get 250 minus 20 minus 128 plus 16. We add all this together, you get 118. Coming over here, this one's a little easier if you remember your trig, so maybe not easier for some of us. Antiderivative of secant of x tangent of x is going to be secant of x, evaluated from negative pi over 4 all the way to pi over 4. So what does that mean? That really means secant of pi over 4 minus secant of negative pi over 4. And yeah, let's draw our triangle. So it is pi over 4, so it's a 45, 45, 90 triangle. So that's 1, 1, and root 2. Secant is the reciprocal of cosine, right? So if I grab an angle here, that's pi over 4. Cosine is adjacent over hypotenuse. This is going to be hypotenuse over adjacent. In other words, just square root of 2. Minus, okay, now this negative here, I need to wonder, is this going to be positive root 2 or negative root 2? So I write down my all students take calculus, even though they don't. All students take calculus. Let's see here, negative pi over 4 is going to land us here. Cosine is positive, so secant is going to be positive because it's the reciprocal of cosine. So it's going to be positive root 2, and we get, oh, that's just 0. Nice. Okay. Now we get this little word problem involving Mrs. Gilbert. Mrs. Gilbert's filling her pool at a rate of this. Okay, so a few things to notice. First of all, it says rate. The word problem is also nice to us and gave us capital F, okay? That's going to be important. You also see it's gallons per minute. So it's talking about a rate here, like it said, right? And it tells us how many gallons are in the pool at starting, like at the very beginning. And it asks us to find the total amount of water in the pool after 9 minutes. So what I'm going to do is I'm going to set up a definite integral here. And, well, rewind. What is going on here, okay? Well, first of all, let's pretend there's a function, f of x, that is equal to the amount of water in the pool, okay? Well, what is the derivative of this? Well, the derivative of the amount of water in the pool would be the rate of the water in the pool. And I realize, let's do this. Let's use t instead. There we go. Okay? So remember before we were talking about one of the ways to think of these, one of the things they represent is not just area under the curve, it's also the accumulation of change, okay? That's what we're working with here, okay? So if we want to find the amount of water in the pool, we're only given the rate, we need to worry about how much that rate accumulates. So we're going to need to take the integral, okay? One way of thinking about this is we have the antiderivative, we want the original function. So we need to integrate to get back to the original function, all right? So if we know this is true, that means that the integral of capital F of t dt, that's going to be equal to the original function, right? Which we don't have the original function. We want that. The unfortunate thing is we can't just do this abstractly because we would get a plus c here, right? We wouldn't know what the constant is. We actually kind of do know what the constant is, but I'll talk about that more later. Instead, we want to do a definite integral, and we have the total water in the pool after 9 minutes. So we want to start at 0, start when she starts filling the pool, and go all the way to 9 minutes. Okay, what this will let us do is this will let us get a definite integral and get an exact value for how much water came into the pool over the course of 9 minutes. Remember, it's an accumulation of change. We only have the rate. Well, we can calculate how much is changing. And if you say, well, the rate, can we just multiply that by 9? Well, yes, we could if the function was something simple like f of t equals 20. Then yeah, 20 times 9, that's how much water is in the pool. But we don't. We have something that's changing over time, okay? As time increases, the flow rate increases, okay? Don't ask how that works. Sometimes things like that happen, right? So we can't get an exact value. In fact, if you make a graph of this, I'm not going to go too deep in this, but you make a graph of this, it's going to be curved up a little bit, right? It's going to look something like this. So we don't have an exact value. We're looking for the area under the curve. But yeah, let's go ahead and just take the antiderivative, evaluate, and see what happens. So let's see here. We have the antiderivative. Let's actually write it down with f of t. So of 20 plus 4t to the 1/2 power dt. And the antiderivative of this is going to be 20t plus 4. Okay, let's raise t to the 3/2 power, add 1, divide by that number, and we're evaluating that from 0 to 9. All right? So, nice thing to remember about 0 is you can plug in 0 there, okay? And you see from plugging in 0, we'll get 0, so that'll be nice. But let's just write it down just for the notes' sake, okay? So, excuse me, we have 9 to the 3/2. Ooh, that's nice because we have a square root of 9, then cube. That's going to be nice. Let's actually flip this. Let's make this, sorry, I'm rewriting all this here. Let's make it, instead of 3/2, let's multiply by the reciprocal. So 2/3 times 4 is 8/3. So we get 8/3, 9 to the 3/2. That's all evaluating 9 in. Then we need to plug in 0, which will be a lot faster just because we are, 1, we already have it set up, and 2 is just 0, so all of that's going to be 0, okay? So 20 times 9 is 180. Here, so we have the square root of 9 is 3, then cubed is 27, then we divide by 3, so it's back to 9. 9 times 8 is 72, minus 0 over here, so we get 252. 252 what? Well, 252 gallons are added over the 9 minutes. So what? What's the question asking for? It's asking for the total amount of water in the pool. And we have to remember that we started with 500 gallons of water. So 500 plus 252 is equal to 752 total gallons of water. Okay? Let's make that a little nicer. There we go. All right. So the total is 752 gallons of water. And probably the quickest way is that definite integral. Another way perhaps to do this would be to find the antiderivative. And if we found that, I'm going to do this actually over here in a different color. If we found that instead, the indefinite antiderivative, indefinite integral, what am I saying? Indefinite integral, you could have done this and we would have gotten this formula, but the problem is we would have gotten, so let's see here, we had 8/3, t to the 3/2. We would have gotten this constant plus c. And remember, the constant is kind of, we're not sure what to add. But in this case, we know that at time equals 0, there was 500 gallons. So we could have said, oh yeah, c is 500, right? And that would have actually been fine. That would have worked out for us in the end. I think it's much safer to do the indefinite integral. And you would have gotten the same answer as well, okay? So hope this helps. Hope this makes sense, especially this bit about the accumulation of change, recognizing when you have a rate. And if you have a rate and it asks for the total amount or accumulation, then you need to take the integral of that and take the definite integral. All right? Thank you guys for watching.